back to ROBT402 Robotic Mechatronic System Design course, Lecture 9, PLC Programming with Ladder Logic, or LAD. Today's topics are as follow: Introduction, Programming Binary Logic Operations with LAD, Programming Memory Functions with LAD, Programming Queue Boxes with LAD, Programming EN or enable in, enable out boxes with LAD, program control with LAD, LD programming example and LD programming exercise. I recommend you to install TIA Portal so you have a video, separate video, and lecture notes so you could follow and install the trial version of step 7 for TIA Portal. This slide and this video is based on TIA Portal. I will create a separate video based on the Codesys environment, PLC programming environment. But this video is based on TIA Portal. So you could install it in conjunction with this slide. As you proceed, you will be able to see the environment of TIA Portal. LAD is used to program the control function of the programmable controller. So again, LAD is ladder logic program. The icons in the toolbar, okay, so one here, can be used to set the display of the working area, the interface of the block, lists the block parameters and local data. The favorite bar can be expanded by additional program elements, so you could add more elements here. Each block has a heading, the block title, and the block comment here, which can be used to explain the function of the block. These are followed by the first network with its number, heading, and comment. So here we have the first network that you could have your number, heading, and comment. So you may wonder how we could have this environment, how you could bring it up in the TIA Portal. Don't worry, as we go forward and reach to the example, you will go step by step. You have step-by-step instruction how you proceed and how you could basically create a new file and bring up exact environment. So this is an introduction to the TIA Portal. You see the environment, but you could review these slides later as you go through the example. Okay, so again we continue with the numberings. Here we have the control function, i.e. the interconnection of the program elements is displayed in the working area. So here, okay, so these are control functions. The tags can be displayed absolutely, symbolically, or with both addressing types. Number 7, so we have these tags for each program elements, either contacts or coils. Each coil and each box can be assigned a free-form comment. So here you could basically add the comment to each tag or contact or coil. The tag information, okay, so here, sorry, this here comment, the tag information number 9 shows the tags used in the network with the tag comments, like the network comment and the free comments. It can be hidden. Okay, with the zoom setting, here you could zoom in. The display of the control function can be adapted to the size of the working area. So again, it might be a little bit confusing at this point because you haven't most likely installed the software and you don't know how you could bring up this environment. Again, this is an introduction, a very good reference point. Later, when you go through the example, once you have your TIA portal installed, and you could back to these slides and review what are the components of the programming environment. Ladder logic program elements. We have contacts, which could be, for example, binary tag. Have coil. Okay, so this is again could be a binary tag. So contacts usually are input to the system. Okay, usually. So for example, you have a switch, you have a sensor, and all these informations are in the form of contact in your logic programming. And then you have some outputs, and usually those outputs are in the form of coils. For example, you have a motor, you have a pilot light. Have boxes with Q output. So Q means that basically it's done. Okay. So it's done. For example, we have a timer, and when the timer is done and finished, then the Q output is 1. So Q is output. We don't use O because O is misleading, and sometimes we get that mixed with 0. So we use always Q. Another box is box with EN input and ENO output. So when the function is enabled, then we have this enable O output, which is true. So we know that the function now is enabled, is working, is in function. It might not be done, but it's activated, it's reached to this function. And we could have a block call. So in this block calls, I could say we could customize or block and add as many as input and output with different functions. Programming binary logic operators. Normally open contact. So is a normally open contact when the input is 0, the contact is 0. When the input is 1 or true, the contact is true. Normally closed contact, it's basically a negated contact of a normally open. So when for example, let's say that this contact represents a push button. Once that push button is not pressed, so the push button is off, then this contact is true because it's negated. So this contact is normally closed because it's true unless you press that switch. It's opposite of just a normally open contact, or simply from the logical point of view is a negated contact. Have a not contact, whatever is the input to this contact could be, for example, true, then the output will be false. And if the input is false, the output is true. So you see that the not contact doesn't have an associated tag, so it doesn't represent a real, for example, input sensor switch to the device, but it just change or negate the logic we have here on the left side of the contact. Okay, so in the wrong, whatever is the resultant logic will be negated. Have a positive edge of the binary tag and a negative edge of the binary tag. We compare the binary tag with the edge trigger flag, and this is the negated version. We will have example of these ones later and the explanation later in the coming slides. Scan for valid and scan for invalid. Okay, so for example, we want to see if a float point tag is okay or is not okay, so we could have a condition for that to see if the floating point tag is okay based on our condition or not okay. We could have a comparison function and we compare the digital tag data type with the digital tag 1 and digital tag 2. Okay, so here we have equal or unequal, greater than, less than, and other basically inequality functions here. Okay, so here we have a nice example programming binary logic operation of normally open and normally closed contacts. And we want basically to have a program that works based on this description. So when press the start and stop push button switch, the fan on and off, they are one active signals. If fault becomes active, the fan is to be switched off and remain off. Fault is zero active signal. In order to reset, the SR, which is set reset function, with signal state 1. The input is scanned with an NC contact or normally closed contact. Scan for signal state 0. In the example, the zero active signal is defined by slash in front of the name. So you should be remember the symbols, IEC symbols for push button switch is normally open and normally closed. This is the normally closed one. So if I want to say briefly what I read here, we have 3 switches, start, stop, and fault, and each of them has one address in the memory. For example, when the start button is not pressed, this I1.1 in the memory is 0. So I represent input and 1.1 is just the address of these switch, or is a binary in a memory. Okay, so we have one contact which represents this start button. If we press the start, the contact will be true and it will set this set reset box. Once the box is set, the output also will be true and the fan will start to work. Now let's say we want to stop it. Okay, so we press the stop button, it will reset the set reset box. The output of the box will be false and the fan will turn off. Okay, now also we could have a fault, which is, you see, is a normally closed one. So normally this one is false, but if for any reason and based on basically any function that we have for this contact, it might not be stated here, could be a different network, But anyway, if a fault happens, then this contact will be true and it will reset the set reset box and the fan will be off. Series and parallel connection of contacts. We have two pilot light here and we have two fan, and we want to see based on the program what each pilot light will show us. So here, if the fan 1 works and fan 2 doesn't work, so when the fan 2 doesn't work, negated means that this contact also is true. So this one is true and this one is true, and the pilot light will be on. So it means that one fan, at least fan 1, is working. Okay. But if fan 2 works at the same time as fan 1, then this contact will be false. And the pilot light will be false or will be off. So if both fans work at the same time, this pilot light will be off. And this is basically for opposite, if fan 1 doesn't work but the fan 2 works. Okay, so either this branch or this branch could turn this pilot light on, and this pilot light only goes on when one of the fans works. Okay, so here we basically have exactly same program, but you see that it's slightly different in the terms of illustration or the networking or connections. But anyway, we have two parallel branch here, and on each branch we have two contacts in series. T branch, open parallel branch. Okay, so here we have the same network. However, here we have a T branch and we have a NOT contact. So when, for example, fan 1 works, okay, or fan 2 works, both, yeah, either of them, then here before the NOT we will have true. We will negate it and will be false. Then basically clock 2 Hz is for flashing with 2 Hz frequency, and then this display will start to flash. Okay. Okay, so if this works, we have true here, we'll have false, and then this clock doesn't work because it's false, and then it doesn't flash. But if any of them stop working, okay, then here we will have false and we'll negate it to true, and then we'll start flashing. Okay. Edge evaluation of binary tag. So here we have an edge contact, let's say, and you see that where you could find in the basic instruction of TIA portal, where you could find a positive or negative edge contact. The edge contact has the signal state 1 for one processing cycle if the signal state of the binary tag's position above it changes from 0 to 1 for P contact rising edge, or from 1 to 0 N contact falling edge. So let's say here we have a tag. Here we have another example here. Here we have a tag at the top, and if this, for example, this tag alarm bit changes from 1 to 0 or 0 to 1 for one cycle of scanning only, not permanently. Okay, so it could be, let's say, 1 millisecond. Depends on the PLC scanning cycle frequency. Let's say for 1 millisecond, the contact will become true or false based on the type of P contact or N contact. Now we have another tag underneath. The edge trigger flag is present underneath the edge contact. This is a memory or data bit which saves the signal state of the binary tag. So the signal state of the binary tag will remain in this tag underneath, okay, or the edge trigger flag. So we always compare this one to this one. For example, this one is 0, and once the state of this one changes from 1 to 0 for one cycle, it will become false. Okay, so this is basically a reference point for us. Why is it good? Because, for example, we have this set reset box and we want to set it once and that's it. We basically don't need the signal, the logical signal here, either true or false, and this box will stay true and the Q output will stay true. Okay, once, for example, we acknowledge it with another push button, then we could reset it. Validity check of a floating point tag. The OK contact is closed if the tag is valid. The not OK contact is closed if the tag is outside the permissible value range. So we should have a range, and based on the range, if the value of our floating point tag is not for the binary falls into that range, then the output will be true, otherwise will be false. Programming binary logic operations with comparison contact. Compares two digital values and outputs a binary signal. In comparison, which is correct, is equivalent to a close contact. Current is flowing through the comparison contact. The contact is open if the comparison is incorrect. So we could have a variety form of data, could be integer, be double integer, real, byte, word, and so on and so forth. Okay, and we could compare or tag with, let's say, a lower limit or upper limit. So, for example, here, if the temperature is more or equal than the lower limit, then the output of this contact will be true. And you could see basically a wide variety of comparator operation contacts, and use either of them based on the program. Programming memory function. Again, before proceeding further, again, I want to remind you that these slides might sound confusing at this point because most likely you don't have the TIA portal installed. I recommend you to install it same time and then try to open the TIA portal, look at the environment, and then also when you reach to the example, and once you are going through the example, back to these slides and review what I explained. Okay, so here for the coils, we could have a regular coil or we could have a negated coil. Same as a contact, could be a regular normal contact or could be a negated contact. Could have a set coil and could have a reset coil. So what is the difference between these two? For this simple coil, the logic behind this coil should be always true to keep the coil true. However, for the set coil, you just need to have a true logic here once for one cycle, and then this coil will stay true because you set it once and you don't need to basically keep that pushing and running. Okay, and once you want to reset it again, you should use reset coil. You could have a pulse on positive edge, as I explained, coil, and variety of other type of coils that I don't want to explain at this point, but we could back to these later. But for either coil or contact, we could have two type of instruction or programming element. It could be either schematic or it could be IEC. So schematic one, you could find it under on the legacy branch. On the legacy branch, you could find the schematic one. So those are the one that works only in the TIA portal, or at least instruction of that is a structure only in the TIA portal. IEC one are based on the standard of the IEC and are similar to those ones that you could find on other PLC programming environment based on the IEC standard. For example, in the codices, most of the functions are based on the IEC standard, so you will find at least a similar structure for those type of commands. Simple and negating coils. Let's go through this example and see what are the differences between them. Okay, so in this program we have two fans, and here at least I could see one display for no fan and one display for console 1. So let's see what are they. So if the fan 1 works, so this one will be false, and fan 2 also, let's say, works, then this one will be false. This display no fan, okay, so will be off because they are working. But if they don't work, this one will be true and this one will be true, and then this one will be true. So no fan is working. So now this one is working. We have this clock 2 Hertz for 2 Hertz frequency, and then this display will start flashing. Now, if either of them works, then the display 1 fan will be true, and then the display console 2 will flash. And here, if both of them work, then the display 2 fan will be true. Okay, so simple. It shows how you could have a series and parallel branches and how you could combine normal and negated contacts to activate different type of coils. Set reset coil. A set or reset coil is used to assign signal state 1 or 0 to a binary tag in the case of a result of logic operation 1. A result of logic operation 0 has no effect. So here, fan 1, let's say, is enabled, is working, and the fan 1 start is pressed. Now we could set the fan. Okay, so I don't know what is this fan 1 enabled. Let's say could be a main power to the system. Okay, so this one is true. You press the start button, then you have true. Now you have a true logic here on this rung here, so you could set it. You could set the first fan. Now if you release this start, let's say this is a push button, if you release it, then this fan 1 will keep working because you already set it. Although the logic here will turn to false, but the fan 1 is already set and is true and is working. Now if you press the stop, even momentarily, okay, you will reset it. And if you release the stop, you already resetted that, so it doesn't work and it turned off. Okay, another type of contacts are retentive response due to latching. We want to see what is the latching here. So here we have fan 2 start. So let's say we press the start button of the fan 2. And stop button is not pressed, so this one is true and this one is true. Now fan 2 drive is working. So see the difference here that we are not using set reset contacts. This is just the regular, coil. However, here we have a contact associated with the coil. So when the start is pressed and stop is not pressed, the fan 2 drive will turn on and this contact also will be on and will keep the logic true here. So even if we release this start push button here, then the logic will stay true here, the fan 2 will be true. So this form of instruction is called the latching. Here is reset is dominant, so the stop is dominant, and if for example we press start and stop button at the same time, the stop button is dominant and the fan 2 doesn't work. Here also we have same form of latching because we are using a contact associated with the coil. However, you see that the place of the stop is located inside the branch. So in this form, if we press the start and stop button at the same time, the fan 3 will keep working. So we say that the set is dominant or start is dominant. So latching is form of retentive information. Okay, it's similar to setting and resetting. Okay, so we continue with programming memory functions. Another type of memory functions are edge evaluation with pulse output, which I explained it briefly, but here in this slide we have one example of using edge evaluation with pulse output. At the top of either with the positive edge or the negative edge, we have a pulse flag, and on the bottom we have edge trigger flag. So when the pulse flag goes from let's say 0 to 1, we have a pulse trigger or positive edge output, and for one cycle only the output will become true. However, each trigger flag will keep the last state of the pulse. Okay, so in this example, you could see that, for example, when the measurement register is true or becomes true, then for one cycle, the coil will become true only for one cycle, and the measurement load EM will keep the last state of the measurement load. Multiple setting and resetting, filling the bit array. At the top we have start tag, and on the bottom we have number of tags. For example, here we have 16 number of bits. So here we have 16 bits, and it starts from the data lad alarm bit 0. So here we could set 16-bit at the same time, 16, for example, alarm bit or a pilot light or motor, whatever is the output, and we could also here, for example, we could reset 8-bit at the same time. Programming queue boxes. On queue boxes, one type is SR memory box and RS memory box. The difference is that set is dominant here and the reset is dominant on this one. We have evaluation for rising edge and evaluation for falling edge. So rising edge means that we are going to go from 0 to 1 on the click, and when that happens, then the queue will become 1 for only one cycle of the PLC scanning time. We have semantic timer functions and we have semantic counter functions. So semantic ones are legacy ones are different from the IEC one. When it comes to the timer and counter, I will explain them in more detail. Programming queue boxes. With queue boxes, the first binary input, and in certain cases, the associated parameter must be connected. Connections of the other inputs and outputs is optional. So you must have one input connected, but the others are optional. The binary inputs of queue boxes cannot be directly connected to the left-hand power rail. When raising queue boxes as program element, you can program one single box per network, either within the current pass or as its termination. Arrange boxes in series by connecting the queue boxes of one box to a binary input of the following box, and position boxes following T branches and in branches which commence on the left hand power rail. So again, these details might be a little bit confusing at this stage because you haven't started to get your hand dirty with the software, but these are very good reference points later when you want to back and read the detail about these type of boxes. Memory boxes in the ladder logic. So in the TIA portal, again, all these examples are based on TIA portal. Under bit logic operations, you could find some of the boxes like RS or SR boxes. So in this one, you see that we have SR and RS boxes in series, and you see that we have a set connected to the left hand rail directly, and the reset on this case is connected to the queue box. So one of them should always have a contact or connection. The others are optional. We could have either that contact or not. Here, on this example, we have a set reset boxes, and you see that how we are using a bin input and bin memory in series to set the box or reset the box, and also for these cases. Edge evaluation of the current flow in format of the queue boxes. We had in the format of the normal contact and coils, but here is in the format of queue boxes, positive edge or the negative edge, and you see that you could find these under the bit logic operations. Here you have one example of using a p-trigger plus we have these comparators to compare the temperature with the upper limit. If that happens, then the click goes from 0 to 1, and momentarily the Q will become true and it will set the SR Q box. Okay, and then basically we could proceed. Once that happened, then this one will become true and we could set the second box. We could acknowledge it to reset it. This is just one example to show how we could use these type of queue boxes. Programming enable in, enable out boxes. Again, on this one, we have enable also input and enable output. Enable means that the box is active, but it doesn't mean that the box is done. Okay, so the output of the box is Q, but to enable, so basically we need to enable it. So the click here, for example, on this one, on the edge evaluation, the click could go from 0 to 1 or 1 to 0, but it doesn't change the status of the output unless we already enable the box. So the box should be enabled first. Here the box is enabled, and then once the click have format of the rising or falling edge, then the Q status will change. Plus, we could check the status of the box, if the box is enabled or not, by enable output here. Some of the other functions in the format of enable in, enable out boxes are transfer functions, or arithmetic functions and math functions. For example, sine, cosine, tangent, move, add, multiply, division, etc. Conversion from one format to another, conversion function for time values, and conversion function for strings. Shift functions, logic functions, and strict functions. Plus, we could customize a box or function box. Edge evaluation with enable in, enable out box. Here you see that you could drag and drop it into your rung. Once you've done that, then this call option window will pop up, and you could choose a name to have an instance of this specific data block and function. you just give it a name, press OK. Now you have a data block in your memory underneath of the data block tree, and you could basically use it. So for example, here you have a start button. Once you press the start button, it goes from 0 to 1. This box will be triggered and the Q output will become true. For the transfer function, you want to basically transfer some data, which is here messages, to some to the other part of the memory or some other bits or bytes. In this case, we have alarm bits, and by the move we could do so. However, the box doesn't work constantly, so we don't move the messages constantly to the alarm bit unless you enable it. So once you enable it, the box will start to function and connect the input to the output as it is intended. Arithmetic functions for numerical values and time values. So here, for example, we are subtracting int2 from int1, and we are transferring to the output temp int. We need to enable the box to be able to subtract these two numbers, and we have the rest of the program. Yep. So under the math functions, you could find all of these boxes. For the time value as well, the same. You could compare it, or you could subtract it, or you could apply different type of arithmetic functions. For the math functions, square root, natural logarithm or exponential, and so on and so forth. And we have a conversion function. You see that under conversion operation, you could find them. For example, you could convert a real type to dint or dint to BCD32, different type of formatting. Shift function that you could shift the quantity by a specific number of bits and binaries. Have logic functions for word type, so word logic operations underneath. You could find XOR, or, and etc. And functions for strings, concatenation, for example, and other basically operations that you could apply on string. Okay, so program control. So far we discussed about the different type of contacts and queues, queue boxes, and enable out. What about program control? How we could control the flow and the sequence of our program? Here we have jump functions, so we could jump to a specific network. Could have a jump list or a jump distributor. We could have block calls, and we could have a block end function. We'll have some of these examples or some of these boxes as we go through the example and exercises, and you will learn more about them. Okay, so jump functions, we have jump, jump end, jump list, and switch. That here, if you choose the program control operation folder and expand it, then underneath we have a jump, and you could drag and drop it. and you could either choose between jump and jump in. Um, so here, for example, you see that the label of this network is max search. Okay, so we have this label here attached. Once we reach to the jump, it will jump to the label, which is the max search, and the program will start over from here, not from the beginning. Block call functions. We could call any block functions that we already program, and we could create as many as instances of that block function as we wish, and we could call them inside the program. Block end function that we could have a return true, return false, and return value. So based on the type of the block end function and the flag attached to the coil, then we could basically return the function. For example, here return, it is the current result of the logic operation. RLO, the current flow, i.e. signal state 1. So for example, here when the logic before this RET or return is 1, then the function block will be terminated and will return the value. Otherwise, it will stay inside the block. Return true, it doesn't care about the logic behind, but it will care about the state of the flag. If it's true, it will return, otherwise it doesn't return, and we have a return false and return value. Okay, so far we review briefly a different type of contacts and coils, different type of functions in TIA portal. Now you have a general overview of what we should expect from the functions in the TIA portal. From here, in the real lab, you used to start programming the distribution station. However, you don't have access to that station, but you could use the PLC sim. We used to basically leave these parts to students inside the lab, and students used to go through these examples by themselves, but I will go through these slides once and quick because you don't have access to the lab. I'm not there to help you, so I'm gonna basically read it quick. Programming the PLC in the distribution station to perform a simple task. Make sure that the PC you are working with is connected to one of the switches in the lab. So you don't have that real PLC, so you could skip this point. Change the IP address of the PC to the one which is determined, referring to the label attached to the case of the PC. So you should always set the address of the PC to match with the address of the PLC. You do this in order to have access to the PLCs of the MPS 500 and be able to program them. For example, if one PLC has address of 10.1.1.2, then your PC should have the same format of 10.1.1.2. for example 3. Then your PC will be able to communicate with the PLC. Again, you are not using a real hardware, so you don't need to be worried about this part and you could skip it. Keep in mind that with the IP assigned manually, you will not have access to internet. To have access to internet, you should use the automatic IP assignment of your PC. Run the TIA portal and follow the steps in the next slide to create your first project. So again, the first 3 bullet points are important on a real device. Since you're using PLC SIM, you don't need to be worried about them. Now from the next slide, you will start to open the TIA portal and create the project. So far you should have installed the TIA portal on your PC. Create an empty project and call it distribution exercise 01. So here, create new project, give it a name, give it an address, and proceed. Now you need to select configure a device. Why you need to do so? Because the TIA portal should know what is exactly the type of the device or the PLC. So the device that you have in the TIA portal should match your exact device. Yeah, you don't have access to the lab, you don't have access to the PLC. However, you need to know how to configure it. Plus, it is a necessary step, otherwise you cannot start programming your PLC even with the PLC SIM. So I strongly recommend you to follow these steps to learn how you could configure your device. Okay, so you choose add new device, and from here, controllers, you need to select yours. But what is our PLC? This is the type of the PLC we have. So try to configure your PLC and device based on exactly these slides. Locate CPU 1512SP F1PN here. In the list of controllers, select the article number as exactly this and the version as V2.0. Okay, this is a version of the firmware for the PLC, could be 1 or 2. This is the PLC which is installed on the station and you are going to use. You could select, of course, other type of the PLC once you are using PLC SIM. It doesn't most likely create any issues, but I recommend you to follow these slides to learn more about modular PLCs, input outputs, and how to configure the device. Then click on add in order to add it to the project. Okay, so click on add and you will add it. The PLC is now added to the project. So if you see in the TIA portal, you see that you have a PLC. Racks are empty. This is a modular PLC. Racks are empty for the input and outputs, and you need to add them. If you want, you can change its name by clicking on the name here and type your desired name. As you inserted the PLC, a rack is generated and the PLC is put into the first slot. So here we have a slot 1 here. See the number. Now you have other slots empty and you need to fill them. The PLC comes with an integrated Profinet interface providing 3 LAN ports. So you see that this one matches exactly with the real device as we reviewed in the previous lecture. Adding the I/O modules or input-output modules. Now you need to add the I/O modules to the project. Keep in mind that the I/O modules are already physically attached to the PLC in the control cabin. So again, we are configuring the exact device as we have in the real world. You should add 2 DI digital input and 2 digital output modules. Why? Because in the lab we have exactly 2 digital input and 2 digital output modules. In the search bar of catalog type DI8X24 VDCHF. Why this one? Because again we have exact same module in the lab, and press enter. Choose the module and select V2.0 as the version, then drag and drop it into the slot 2. Okay, so drag and drop it here in the slot 2. Same, you need to basically choose the same input for the slot 3. Because our system includes 2 digital input modules, each one having 8 inputs of 24 volt DC. Therefore, you can have up to 16 discrete inputs in total. You should add 2 digital output or DQ module. Now, in the search bar of catalog, type this and press enter. Choose the module and select version 2 as the version of the firmware and drag and drop it into the slot 4 and 5. Okay, now your project should look like this. The rack including the PLC with the Profinet element, and the I/O module should look like below. For the second digital input and both digital output modules, make sure that the second option is selected. For the potential group, enable new potential group. So here on the general, you need to select that. Why? Because again the real hardware have this feature, and you should have exact match of the real hardware. Again, if you use a PLC sim, you won't encounter any issues most likely, but when you want to download your program to the real PLC, then you will get the error because your device doesn't match. We need another module in our lab. In the last slot, you should add 1 server module to the project as it physically exists on the rack. In the search bar of the catalog, type this name and press enter. Choose the module and select V1.0 as the version and drag and drop it into the slot 6. Okay, here we have version, here we have the module, drag and drop it here. Now it looks like exact device we have in the lab. Defining PLC tags. In order to have access to the digital input and digital output channels, you need to define tags with proper addressing. In this lecture, we are going to initially use the following input-output elements: inputs, start bottom on the panel and stop bottom on the panel. Output, swivel drive to magazine, swivel drive to downstream stations, LED display of the start bottom on the panel. We have a video of example. I will put it on Moodle. Plus, I recommend you again to watch video of a distribution station to understand what are these components. To define the tags for these input outputs, first add a new tag table. So here PLC tags, and you need to define a new tag table. Rename it as IO tags by right clicking on it and choosing rename. Okay, defining PLC tags, add the first tag by double clicking on add new. So here on add new, and use start button as the name and I1.0 as the address. The variable type will be Boolean by default. Why exactly I1.0? Because on the real device, start button is attached or connected to this input of the PLC. If you are using PLC, you may want to choose any other addresses and still it works. But just to avoid confusion, follow the exact instruction that you have on lecture. Okay, so again, the real device start button is attached to basically the first input. Provide proper explanation in the command section for the tag. So you could basically write start push button on the control panel or any other explanation you wish. Now proceed and add the following tags with the given addresses in a similar way. Stop button, swivel to magazine is output, is the motor, swivel to downstream is again is motor, and start LED. Okay, and you have comments here. Now you have your tag table ready. Now you want to start to write your PLC program. Double click on the main OB1 to open it. This is the environment that you wish to see, and on the network one you could, for example, drag and drop one contact here and associate a tag to this contact. Now click on those question marks and give it a name or choose it from a tag table. So you want to associate a contact with the start push button on the control panel, therefore click on 3 question marks and then click on the browse icon to open the list. Then choose start button and press enter. The name of the tag and the address will be displayed on the contact. Complete the program as given below. Okay, so have a start button, stop button, and start LED. To create a parallel branch to the start button, first click on the left side of the code. Okay, so here, if you click on this one, you could create a new branch, and then you could add your writing PLC program. So we continue with writing the PLC program. Okay, so after adding a normally open contact, drag the arrow on the right and drop it after the start button contact. So here, so you already added the start LED. Now you could connect it here. So you have a parallel branch, and notice that we did the latching. So we have the same address of the coil for the start LED in the contact here. Now we could add the second network and complete the code as shown below. Here on this network, once the start LED is true, the swivel will basically will move to the magazine station or the magazine side, and this one is negated because these two are antagonists. They cannot work at the same time. We cannot swivel to the magazine at the same time to the downstream. So one should be off and the other one should be on. So when the start LED, for example, here is on, then we swivel to the magazine side, and the other motor or actuator is off. And once is false, this one is false and the other one is true. Look, we created the second network. However, we could include these part of the program or the drawing in the same network. Why we need to have two? It's not necessary, but what we could do, we could put a comment, we could put a label, we could jump to the network. So it's a good practice for programming, not necessarily not necessarily change um, the behavior of the program. Connecting to the actual PLC, the first step in connecting to the PLC is to set the correct IP address for the PLC in your project. The IP address of the PLC on the distribution station is 10.1.1.2, and you need to set the same address for the PLC in your project. So you see that where you could in the project set the correct address, IP address, but again, if you use PLC SIM, it doesn't really change differences here, so it doesn't make any differences. Double click on device configuration, then on the Ethernet port of the PLC, and then change the IP address. The IP address of the PC should also be compatible with the IP address of the PLC. To have direct access to the PLC, use a LAN cable to connect your PC directly to one of the PLCs on the MPS setup. Look, you don't need to connect it because you don't have the device. Before connecting to the PLC, you will need to compile the hardware and software of the project. Right click on the name of the PLC here and select compile, and then hardware rebuild all. If you don't get any error, it means that you had a perfect configuration of your hardware. Then you could repeat it for the software, and if you don't get any error, it means that your program is flawless and perfect. At least it doesn't have compile error. It could have some errors in terms of the logic of the program, but not the compile error. Now right click on the name of the PLC in the project tree and select download to device and then hardware configuration. So once you are connected to the real PLC, we'll download the program to the real PLC. However, in the PLC SIM, if you open the PLC SIM, once you do the downloading, it will proceed with the downloading, but to the PLC SIM, not to the real device. If this is the first time that you want to connect to the PLC, you will see the window below asking for details of the connection. Okay, so here you should see the detail of the connection. Click on the search to see all the PLCs connected to the PC or to the network. For example, on MPS 500 we have 5-6 PLCs, and if you do the search, you will see all of these PLCs here. You will select your targeted PLC and then you will load the program on that. If the IP address of your PC is not compatible with the PLC, which is most probably the case, then you will receive this message. Click on yes, and the new IP address will be assigned to your PC. Most likely you won't encountered these issues on the PLC sim. Click on OK and then click on Load in the new window. And then remove the tick in Start All and then click on Finish. So what is this Start All? Once it downloaded to the PLC will run the program and will go through the cycle and will execute the program. Once this Start All is ticked, but if you remove this tick and then you need to manually run the PLC later by yourself. Okay, so now to download the software into the PLC, right click on the name of the PLC, then choose download to the device, then software all, and then load, and then start all if you wish to basically start the PLC right away. Now, to monitor what's going on in the PLC, even in the PLC sim, you need to click on Go Online. So when you click on Go Online, you will keep the connection between your PC and the PLC and they will communicate. And you could at the same time monitor what's going on in the PLC. If you see all of these ticks on the hardware configuration, it means that you have a perfect hardware match and you don't have any issues from the hardware point of view. Okay, now open the main program and run and turn on the monitoring. This is the monitoring. If you double click on these glasses icon, you could turn on the monitoring, change the state of the start and stop push buttons on the panel and observe the operation. So in the real device, if you click on the start, then this one will go to the solid green as you could see on the stop, because this stop button is a normally closed contact, but this one is a normally open. But in the PLC sim, you don't have access to the device. So how could you change the status of this start button? You just right click on this contact, choose a modify to, for example, 1 or 0, and then you could change the status of the contacts in the simulation. Okay, it's a bit difficult to test the program in PLC sim because in a real device you have so many sensors and inputs, and you need to understand the sequence of which one first should be modified to either 0 or 1, and then test your program step by step as you proceed. So once you have this dotted line or blue contacts, it means that the state of them are false. And once you see these solid green or green lines, it means that the state of these parts are true. Okay, first exercise, distribution exercise 1. Now it's your turn to write your own PLC program to perform the following task. So I expect you to do so in the PLC sim, although it's a bit difficult to test it in PLC sim, specifically with the ladder logic. But since this program is not that, let's say, lengthy and complicated, I think you will be able to test it in PLC sim. You would need to define new tags referring to the I/O devices or some internal codes. The PLC program will be based on the previous one, and you need to extend it to perform the following task. So if you manage to follow the example and programming in your TIA portal, then you could build on top of that to make it as it is requested here. When the start button is pressed, the piston, this is the address of the piston in the real device on MPS 500 in the lab, should be activated to provide a piece. Then the swivel should come to pick the piece. When the swivel is arrived, so we have a sensor, the vacuum should be turned on. This is the output, this is a motor, this is a coil, in order to pick the piece. When the stop button is pressed, the vacuum should remain on and the swivel should transfer it to the next station. When arrived, so we have a sensor. What is this sensor? This is a proximity sensor that checks if the swivel is arrived. The vacuum should turn off and the eject piece should turn on in order to release the piece. So in order to release the piece, basically we blow out air to release the piece from the suction cup. Once finished, submit your project as a single file through Moodle. Use your group number at the beginning of the file. You could do it in a group or you could do it individually. This video shows what we expect from this exercise. So if you do it perfectly in the real device, then you will be able to see this performance. So here, if we press the start button, okay, so the pieces provided, the swivel will come to the magazine, the vacuum, you could hear the sound, the vacuum now is turned on. Now you press stop button and then it will go to the downstream here, and then the air will be blown out to release the piece from the suction cup. And again, we press the start button. You see we have also one LED on the start button. This is LED here. The piece will be provided. Okay, that one is a pneumatic cylinder. It has it's a coil. It has an address in the memory, which is provided in the description of the exercise. Now swivel goes to the magazine. Press stop button. The LED is off now, and then it will go back to the downstream side. And basically it will continue. So we could swivel manually between these two stations to pick it apart. We have two exercises, but I'm gonna keep them optional for both of them because it becomes lengthy if you want to do it in a ladder logic environment, and it would be very hard to test it in the PLC sim. Later when we go to graph programming, you will see that it's quite easy to test the program and write the program in a graph programming environment, even with the PLC sim. However, has a bonus for both of the exercises. If you wish to do so, you could do that and submit it on Moodle, and you will get a bonus grade and point.